Okay, Min, I saw your question. So we'll figure out how to do that. I'm not sure. So either Phil or Dave can help me open up the assessment answers. Okay, so let's move on to okay. So this is an inverse log uh, for the detail placement. So notice here, I want to show is that it's actually move a lot of cells here, right? So it move for this particular run, it moved 5,551 instances. So instance basically is a cells, right? So it moved all these cells from its original placement from global placement, right? So it tell you it moves the mean and max move and which instant it moved the farthest away, right? So it's actually moved cell quite a bit, right? Based on the initial placement, the global placement. Okay, so the reason I put all these locks, native lock in here, so when you do your lab, you can refer to the slide and each step and search for these keywords. Then you know what happened and what happened in each of the steps. Look to the log file. So these are the one highlight. You can search for these keywords. Okay, throughout this lectures. I'll be showing a log file so that you can refer to it during labs. Easy to find things to know what's going on in the in your labs. Okay, so we just got done with global placement, route, and detail placement. So the next things, let's talk about HFNS, high fan-out net synthesis. So what exactly is high fan-out net synthesis? So in your design, usually there are maybe more than a couple nets that's considered high fan-out. For example, the reset is one of the high fan-out nets. So reset normally go through every flip-flop, right? Every flip-flop will get a reset. Most of them, 99% of them. And the other one is the scan enable, right? And then the other one is the clock nets, but the clocks are considered special nets. So we won't talk about till CTS. So here we'll talk about these two nets. So reset and scan enable. So these consider high fan-out nets. So for example, in design that may have 100,000 flip-flops. So your reset ports, assuming it'll go to all the flip-flops, then you have 100,000 um, fan-outs on these nets. So we haven't talked about fan-outs. What is a fan-out? A fan-out is basically a cell that attached to the nets, right? So in this example here, you see 1, 2, 3, 4, 6, 7. There's 3 times it's 21. So in this example, this reset has 21 fan outs. Okay. So in your design, if it's 100,000 flip-flop, you have 100,000 fan out per reset line, per reset port. Okay. So the job of high fan out net synthesis is to break up these fan outs so that it can meet the design rule, the DRV, which is design rule constraints, right? So they're by default, all the design will have specific max fan out number. Okay, so we'll talk about the max fan out a little bit later, but this is the step that actually does that. Okay, um, so take a look at this. This example, the reset has 21 fan out, assuming that the max fan out set for the reset port is 7, right? So after high fan out net synthesis step, the tool insert buffers, 3 buffers here, right? So break it up to 7, 1, 2, 3, 4, 6, 7. So insert buffer here, in first buffer here, and another one here. So basically these 21 will become 7 each for this gate buffer 1, 2, 3. So each of buffer now will have only 7 versus the reset part has 21 before. So this is what happened in high fan out net synthesis. So this just in symbol term in a small, just 21/7. But in a real design, you can have, 50,000 flip-flops. So the process, it goes through the process of just inserting buffers to reduce the number of fan-outs. So during this step, this tool does this on the reset and scan. Pretty much those two nets that I'm aware of. There may be some other nets that's considered high fan-out. But normally these are the two that the tool will go through and buffer up to reduce the high fan-out nets. And filtering, you guys have any other examples for them? I can't think of anything besides reset and scan enable nets as a high fan-out nets.
Yeah, you might ask, will the tool does this automatically based on your max fan-out
Yes.
constraint, right?
Yeah.
What is the difference between this high fan-out net synthesis versus the typical placement optimization based on max fan-out?
Oh, so this high fan-out is basically geared specifically for this purpose, right? There during the so the tool does this as part of actually you go to the loop, it actually does this first, and then because these nets are usually not timing critical, so it'll do this as part of this H2NS. The DOV part that actually it does on a normal step is during optimization. Those nets are usually timing critical, so it'll get done during the optimization step versus just a high fan-out net. The high fan-out net mainly look to break up the fan-out and not consider timing as part of these equations.
Yeah, and you might notice that the purpose of high fan-out net might be making sure that all these endpoints or the points that the high fan-out net reaches to, in this example, reset, right? So this reset goes to every flops here, 21 flops here, and high fan-out net will make sure that the loads are balanced, and afterwards when you do asserting a reset or deasserting a reset, each register might receive the signal about the same time, versus other type of optimization based on high fan-out. They don't have a synchronization goal here. So you see reset, scan enable, blocks, right? It will try, in addition to fan-out control, it will try to do also arrival control, right?
Yeah, thank you, Joe. Okay. Thank you for your input. Anything else?
I want to answer the other question, but
Okay, go ahead.
so the opening up of the pre-assessment, I think I found something and I made a change. If you all can try it and see if you can see the incorrect answer now, then let us know. But I think I found the fix. That's it.
Okay. Oh, thank you. Yeah, I'll pick that from you next time after this. I'll learn how to do that. Okay. Here's a log. The logs from Innovus that show the step of high fan-out net synthesis. It's called high fan-out net optimizations here, the keyword. So if you go through the after you run the placement, you go to the log file, you search for this keyword high fan-out. That should bring you to the step where it does the high fan-out fixing. So notice, yeah, this is pre-CS, right? So you can see after 10 commits, the density went up, so it adds some buffers. Okay.
Another question. So Nguyễn Vũ Thịnh Anh asks, are buffers set according to any rules, or are they just based on the load?
I don't quite understand the question. Do you understand? Do you know how to interpret the question? Phil? Are the buffers set
I
according?
don't understand the question
Yeah.
either.
I
But I
think
can make a general comment. Go ahead.
I think he asked. I think probably he reading ahead, thinking about CTS. So I think what he's asking is the buffer selection. Is there any control over the buffer selection, right? So the tool gonna go and select the buffer according to load. I think that's what he's asking, or is there something else?
Okay. So I see.
Does that make sense?
Yeah. I think what I understand. Um, so during the height train bufferings, right? As far as I know in Innovus, there is I don't think that I mean, you can set, there is a set don't use on specific buffers that you don't want the tool to use. For example, I know I normally go in a design, so there are a specific set number of that drive strings, different buffers that we don't want to use. We know it causes issue, or whether it's can be aggressor, too large of buffers, or too small can be a victim for crosstalk. So we do control the number of buffers, but once those are out, all the buffers that is available in design in the libraries will get used, right? Will be available for high fan out to use. I think that's what hopefully that's answers questions. It's not like CTS where you specify the buffers.
Yeah, yeah.
It's a global.
Yeah, if it is related to high fan out nets, it might be something that if you want to control the use of the buffers that will provide the balanced rise and fall delays, meaning so the most optimal buffer might favor one versus the other, meaning that when you rise to rise or fall to fall, they might have different delays. But if for a particular library, if the if the delays are different and you want to give us more, give the tool more help in terms of buffer selection, you might want to do that. But in general, if you provide a set of buffers, like Bart mentioned, some of the buffers might be too big and you don't want it to use, because if the tool use a big buffer, that means a huge current might go through the buffer and you might have EM problems. So sometimes you want to say don't use those big buffers, and Bart already mentioned about the crosstalk control. But in general, the tool will pick the buffers according to its algorithm. So it will pick the buffers for use in conjunction with other logical gates to give you the overall speed, the delay target. And also, if you put power in your optimization criteria, then it will try to get low power to pick the low power cells versus the high power cells as well. So in general, you don't control the buffer set except for special occasions.
And thanks, and Phil. And you all see, if you look to the log file, you see from time to time, you see what happened is there's a step called area reclaim. So it's go through optimization, it put down buffers and things like that, and then it go back and it filter out, okay, these nets, for example, scan enables or reset line, okay, based upon the requirements, okay, it's not timing control, but it just need to get there in synchronous. It go back and swap out for different cells to save area, so smaller cells, for example. And you go through the log file, you see that happen. Okay, so we're done with high fan out net synthesis. Let's move on to scan chain reordering. Okay, so first, what is a scan chain? But before we get to the scan chain, what is a scan flop, right? So in your design, whenever designs be synthesized, sequential cells will get mapped to normally get mapped to regular flops, right? So it designed what's called 100% scan. So every flops will get replaced by a scan flops, right? A scan flop is a little bit different than regular flops. It still has a clock, but it has a scan in, scan data in, and a data in, and then it has a queue. But some of the flop scan flop will have also this different scan output, right? So this is one type of scan flops. So so your netlist come after synthesis will be just mapped to regular flops, right? So after that, what happened is the netlist will go to a DFT teams. The DFT team basically is called Design for Test Team. There's a separate team that does their goal is their expertise is about DFT, right? So they will insert this the scan flop, which means replace the scan flop with the regular flops. For like 100%, they call it full scan design. Every flop will get replaced with the scan flop. But if it's a partial scan, not all the flops will get replaced. Okay, so that's where the scan flop get inserted is during the DFT insertions. Okay, the DFT team does that. They use a tool that does that. Okay, so now you you kind of know what a scan flop is. So basically, a scan chain is a series number of flip of scan flop that connect back to back to form a chains, right? So this is example of a scan chain. You can see the Q goes to SI, Q go to SI, back to back, back to back. So you have a scan in and then scan out, right? This is called scan path here, right? QSI. A normal functional path is the data path to Q these common logics. So you may ask why we need to insert a scan chain. Well, the scan chain purpose is to identify help to identify mental defects. So mainly in this combo logic, right? So with these the scan defect in this combo logic, so the DFT team will design a patterns that actually send into the scan chain shift sequentially in, and then they'll can detect manufacture defect, either stuck at 1, stuck at 0, and things like that. But those are the different topics. Those are DFT topics, which we will not cover details here. But I just want to introduce you to a scan chain. What is a scan chain? Okay, and why do we need to reorder scan chain? So,
but can I, before you go into the reordering, can I add a couple of notes to help people just visualize, understand at very high level
sure.
of scale? Oh, yeah. So there's a concept of controllability and observability.
Oh.
So when you have a chip with 10 billion transistors, right? You don't have a visibility on what's happening inside a node, from the pin IOs, and sometimes you want to do certain things to have that observability, meaning what's happening in this node inside this 10 billion transistor. So that's observability. You want to see what's happening there. And the controllability is you want to override the internal nodes with certain values and to test what if this happened, then what are the outputs. So the scan chain allow you to do that by shifting from your pins a series of things that will help you with controllability, meaning you shift zeros and ones to these registers and you override those registers with 0 and 1. That means you put the chip in a mode that you understand internally what's happening. So after you shift it in, you you impose those zeros and ones onto these registers, and you execute a cycle, and you shift in the result of that cycle, say a data path or register value or a series of different control signals, and then you shift those out. And then by shifting those out to the pins, and you know internally what those internal nodes are like. So your ability to drive in series of zeros and ones onto your internal circuit, and then observe the behavior after a clock cycle or whatever, what the circuit does. So that's a concept of testability. So the scan chain helps you do that.
Thank you, Phil. The other thing I want to point out is the test time is very costly. So normally the DFT engineer will actually divide the scan chain into equally. So if there is a let's say a 1,000 flops in the design, right? So they may want to break that into 10 different chains. So 1,000, that means each chain will be 100. So that way, you know, all the chains are equal, so it use equal number of cycles through test time. So that's shorten the test time versus you have one chain is 200, it takes twice as long, right? So normally that's what they normally do, is they divide it equally to reduce test time. Okay, hopefully everybody kind of digest that, and also digest the DFT overview that testability that Phil just gave you. Anyway, if not, you can read that up on Google and YouTube. It has quite a bit of material on the topic of testability. It will help you understand a little bit more about scan chain. But anyway, here we just gave you a definition of basically what the scan chain is and understand what it is, and then why, you know, why we need to reorder them. So scan chain reordering is the process of reconnecting flip-flops in the scan chains to minimize wire length based on flip-flop placements. So this can only be done after the detail placements, right? So once the placements are locked in, the standard cell placement are locked in place, then we can do this. Why we're doing it is to help reduce the routing congestions. So here, example, this design, we have 3 different scan chain, scan 1, 2, and 3. That's input scan 1 here, output here. So let's quickly trace to scan scan chain 1. You go to flip-flop 1, 2, 3, come back to 4 here and go out, right? Same thing, let's go to scan 2. You go to flip-flop 5, 6, and it come all the way back here to 7 and then A and out. Likewise, 9, 10. As you can see, this is the connectivity after placement of the scan chain, right? So the reason we order is to reconnect them. So this is after scan chain, so it's shortened the length, right? It's shortened the length, so it reconnect F1 to F10. You can see it's shorter, and then to F6, it moved it to F6, and it goes to F13, come back. So the chain is a lot cleaner, so it's more straighter. So less wiring, less congestions, less wiring congestions. Likewise with F2. So this does not really change any functionality in terms of the scan chain. It just reorder and reconnect the chain differently. That's all it's doing. Okay, you can see the before and after. Okay, so this is a true pictures from Innovus here. You can see the scan chain, the chain here kind of swirly everywhere here. And then after the reordering, you can see a little bit, it's less wiring, straighter, so less congestions. It's not less density, but it's actually less congestions, help reduce congestions. That's one of the main reasons that we do scan chain reordering.
And you might ask, where did the original ordering come from, right? So you want to explain that?
Yeah, sorry. Yeah, the original ordering is based on the DFT, right? The DFT team hook it up. So once they'll give a scan def. So when they insert when they do scan insertions, right, they will connect to a chain, create a chain, but they don't know anything about the placement, right? There's no placement yet. So the chain will get flopped down, whatever it looks like this. So when we load the scan def in, that's where it came from the DFT team.
Yeah, and that DFT team operate and connect these scan chains during the synthesis step.
Right.
So in the old days, the synthesis was not aware of the physical location. Keep in mind, these are physical locations of the flops, right? So the synthesis didn't know the physical locations in the old days. So they order these things based on alphabetical, names or whatever algorithm they have in terms of logical view of the net list. So they say, PD what flop 1, flop 2, flop 3, connected in one chain. So they're not aware of the physical, and then when you go into the physical, the tool place these physical cells according to meet timing or power. So that's when the original order won't make sense anymore, because now you want to minimize the wire length. But modern synthesis tool does what you call physically aware synthesis, meaning that they have their internal engine to do some of these placement, and so they are aware of the physical locations of these flip-flops. So in modern flows, a lot of times you won't benefit from scan reordering as much as before. So just a note.
That's very true. Yep, if you use the physical aware synthesis, then the scan reordering is much less important, or it doesn't help you much if the synthesis is already physical aware. Yeah. Okay. Any questions? No? Okay, we'll move on to the next slide. Okay, so next one we'll talk about DRV, design rule violations. Okay, so in this DRV fixing step, the tool will fix the design rule constraints, which is a max fan out, max train, and max cap. Okay. I think we talked a little bit about the max fan out, but we'll revisit it here. Okay, so one of the rules here is max capacitance. So what is max capacitance constraints? It basically defines the maximum limit capacitance load that an output pin can drive. So this is on an output pins, okay? So these constraints come from the libraries, okay? So each output pin in the library will have a max cap limit. So here is a snapshot of one of the pins. You can see there's an output, and there's a max cap of 0.3349 picofarads. Okay, so here is the example of what it looked like. So it's on this pin, it's a limit that much. Okay, so which means that if this node happened to drive a more load, like along wires and the caps here is going to be, the cap on the load would be the input cap of the pins and the load on the wires, the cap on the wires. So if that exceed 0.344, you violate the max capacitance DRV rules. Okay, so the tool will know that because it read the libraries, right? It read the libraries. It knows is the maximum cap for this cells, this inverters, and then it calculates the RC, the caps here based on the load, the fan out load input caps of these cells, and then and the cap on this net. Then if it exceeds this, it knows to go in and fix it, okay, during the DRV fixing step. So how does it fix it? It can either increase the driver size here, so the bigger cell will be able to handle more, so this max cap limit is higher, or it can break up these nets, just insert buffers along the way to break up the caps, reduce the cap on the output of this guy. Okay, so that's two ways it can do that. In addition, right, this is library constraint, but designers or PD guys, we can add additional constraints by just doing set max cap on the overall design or whatever we want to do. We can set that limit based on what we know about the design, based on the timings and things like that. We can set additional max cap as needed, right? So hopefully this makes sense. So these max caps constraint will get fixed during DRV. Okay, so that's how the tool knows about these and how to fix them. Okay, well, let's move on to the next slide. Next one is max fan out. We touch on this a little bit. So the definition of max fan out is the limit maximum number of cells that an output can drive safely. So similar to max capacitance, this comes from my libraries. So each output pin will have a max fan out. So this particular one has a max fan out of 20. So here on this output of this NAND gate, it has a library fan out max limit of 20 load, 20 fan out. Right. So similarly, based on the max fan out limit of the cells and then the calculations, the tool will know exactly how many loads is on this particular pin. If it exceeds 20, then during DRV, the tool will go and fix it. Okay. So here, fixing it can by adding buffers, so it can drop buffers here and here and here, just like similar to what it was doing in the high fan out nets, right? Drop here and here and here. Will limit the fan out, right? Okay. Similarly, user can also go in and set max fan out limit on particular pins. So here example of set fan out limit of 16 on this particular output pins. And this is just set an overall design, current design. So I don't want anything bigger than 50s. So user or designer can go in and add it there manually on top of the library constraints. Right? Make sense? Okay, lastly, MAC transitions. What is MAC transition? So it is a maximum slew that is allowed on the cell input pins, right? So what is a slew, right? Slew is defined as the time it takes a signal to rise from 10% to 90% of its maximum value. So here is slew. So this is, assume this is 100% of its maximum value. Could be 1 volt or whatever, right? 0.8 volts. So this is 10%, this is 90. So slew is defined the time it takes to go from here to here. Okay. And then the transition time basically is the time it takes the pin to change states. So to go 1 to 0. Okay. So it's also a library constraints. It can also add by designers. Okay. Why do we care about, you know, the MAC transitions and so on? Why it has to be a certain value, right? It asks that because this isn't like all the DRV rules, right? The DRV rules is design rules that is set by Foundry. So if we don't fix these, it impact design's performance and functionalities. So we got to fix all the DRVs, right? So this can also be fixed by increase the buffer size, so to speed up, bigger drivers can drive this faster. They can drive the signal much faster. If it's slow like this, we can drive faster. Also by buffering. So you'll see that the tool will do this by going to the log files. Same things like the other one. You can also set the max transition time on particular node, particular inputs pins if you want. If you think that as particular cells that need a faster max transition time versus the default one in the library, so you can set it by just do set max transition and whatever value you need. Okay, so this is just a snapshot of the Innovus log during the DRV optimization or fixing. So you can see initially here, you can see the max trend, max cap, and max fan out. There's 110 nets and there's 2249 terminals or pins that actually violate. Same thing, you look at max cap, max fan out, right? And notice the through each pass, the number of violation goes down, right? And you can also see that actually it helped the timing, the setup timing quite a bit. So the tool always do the DRV fixing first. So the DRV fixing actually will help your timing, okay? So in this run, you can see it by the end of the DRV ops, it cleaned up all the fan out, max fan, max caps, and max fan out, right? All zero. And then it's also happened to fix all the setup timing also. So this design is not very timing challenging. So by fixing DRVs, happened to fix all the setup. In real life, it's not going to be the case. Most of the time, it's not going to be the case. You'll need to run a timing op loops to fix all the timings.
So there's a question.
Okay.
You ready for it? Okay, so from Khánh Dương, how does the max fan out number, how do the max fan out numbers affect, what is the effect of it to the driving cells? Assuming that there is some max fan out violations, but there is no max cap violation.
Yeah, let me digest and understand the question first. How does the max fan number impact the driving cells, the drivers? Assume there is a max fan out violations. Do you understand the question too?
Yeah, I think I could try to
go ahead and
answer that, right? Yeah. So the purpose of max fan out is to make sure that the current requirements from all the inputs, all the outputs, all the gates that a driver is driving do not exceed the capacity of that driver. For example, if a driver can drive 200 milliamps or 2 milliamps, and you add up the requirements on all the fan out that it needs to drive, and that number exceeds 2 milliamps. So what happens is that you will have harder time, right? So this is divide and conquer too. So by limit the number of fan outs, and you don't violate that, then you know that the choice of driver can be made easily, and so that you won't have a problem of driving a huge load, but you don't have the big enough of the driver. So that's the impact of it. This is very good question, because so say max cap, right? Max cap is the maximum cap that you put on. The reason for the max cap is that when you do a library characterization, as you recall, you have delays versus capacitance and input slew rate. So this also relate to the max slew rate as well, max transition time as well. So when you characterize a standard cell library, each cell will have a delay table that is an input of the transition time and the capacitance it drives, so the load, right? Slew rate and load. So if your slew rate or your load exceed the range, meaning that you have a table, and if your cap is going from 1 femtofarad to 2 picofarad, and your load actually is exceeding 2 picofarad, what the tool does, the delay calculator does is that it does an extrapolation. It's called extrapolation versus interpolation, meaning that if you in the table, then the delays will be calculated based on 2 points that you provide in the table, and it will interpolate, meaning calculating the delays in between by interpolation. So if you within the table, then interpolation is very accurate because you have 2 different points in a nonlinear curve. But if you extrapolate, then chances are you're not going to be very accurate. So all these max cap violation, going back to max cap violations, if you need to meet that max cap violations in order for your timing to be accurate. But you can have no max cap violations and you still have max fan out violations based on the different characteristic of the max fan out, like I mentioned. So I think that hopefully that answered the question.
Okay, thank you, Phil. So the bottom line is that all the DRV rule must be fixed because that's came from Foundry, from pre-characterization data that they know what's each of the cells, each of the drivers, each of the pin can handle, right? So if you violate those, it's gonna impact your design performance, also functionalities could impact your functionality, because if the signal doesn't get there in time and at the specific threshold, then it doesn't register downstreams, right? And then if you latch, instead of latch a 1, you register at 0, then that's going to cause issue. So all the DRV needs to be fixed. Okay. Okay, so actually that's in this lesson number 9. We have about 10 minutes left. That we can probably go over the pre-assessments question, pre-assessment answers, unless anybody have additional questions. So this is just the reference.
There's another question, but
okay.
The question is, in the material video you give us, there is something called spare cell, end cap cell, tap cell. What are those?
Yes, so the spare cells we'll get discussed in later in one of the topics here. But briefly, the spare cell basically are spare cells that we added in. So basically, designer added in, or designer can add up in the front on the net in the netlist, or PD guide we can add it in. So in one of the step in placement step, we'll add spare cells. So spare cell basically the cells that we added in for future ECOs. So if we have functional issue, the cells are already in there, right? So all we need to do is to do a metal ECO. So that way it save the company a lot of money, because each metal layers that you touch, it costs additional money. So that's the reason that we add the spare cells in there, right? And then
But you might want to explain what ECO means.
ECO stands for engineering change orders. So basically, anytime you have a functionality change, or even there's timing ECO and there's all the functional ECOs, right? So spare cells really in there for mostly functional ECO, also sometime timing ECO. So if there's particular data path that actually missed timing, in simulation, everything meet, but in silicon it missed timing or whatever, then it, the buffers or something in the path, you can add, buffer it up. That's the timing ECO, right? So basically, it's a change order you make after you actually, there is a post-silicon ECO versus pre-silicon ECO. Pre-ECO meaning that you can actually, before tape out, you can make a change, right? And then post-silicon is after, and we have to do a metal ECO. That's more costly.
Yeah, and the purpose of it. Oh, go ahead.
No, go ahead, sir.
Okay, so the purpose of it is to enable quick changes in terms of logic or timing fixes without having to repeat the base layers, right? So these spare cells have gates, NAND gates, NOR gates that are really not connected yet to the main logic. And then if you have a change, if you have a functional bug late in the project or after silicon is back, you can do a change in the metal layers, and you can fix functional or timing bugs. So that's the basic concept of it. So you don't change the base layers, right? So meaning that you don't change the end diffusion, the poly gate, and etc., the end well, etc. You only change the metals, so it's a lot less costly, and it can be a quicker if you talk about the pre-tape out ECO.
Right, and if you don't fit in the ECO, you will basically you had to what we call a full spin of the design, and that will take a lot longer to do all the verification, all the placement, all that for the new tape out.
And you have to pay more money for the mask set, right? Because you need to have new masks.
That's correct.
I think the next one, the tap cells so tap cell basically is a well tap cell. So the tap cell is used to prevent latch up, right? So in the tap cell, usually the end well is connected to VDD, and then the VSS connected to P substrates. So tap cell get placed spread across in a column in the design according to specific technology. It requires specific distance to prevent latch up. So that's what the tap cells is. And then the other one is the end cap cell. So end cap cell basically is inserted around the cell boundary to prevent basically safeguard against manufactured damage to a regular cell gate. So you on the Korea, you see the tap cell installed all around. So that's to avoid a boundaries issue to protect the regular cell gates, right? When at the end. So
I want to add to that as well. It's related to characterization. So if this is an advanced topic, but just very quickly so that you kind of aware, when you do the characterization for timing, the surrounding circuitry affects the characteristics of your cells in terms of timing. So you want, for example, if you have poly and you have another poly parallel to it, it will control the process. So your poly will be in certain control that will yield certain electrical characteristics. So if you don't have poly next to it, the process variation will give you a different device. So basically, it's a way to ensure that whatever cells you're using in your design will have the expected electrical characteristics. Yeah.
Okay, so then hopefully that's answer those three, and then
The next question is, how can overflow be calculated? From Ngô Quốc Thái.
that is the that is a topic in next week's in congestions. We'll go over that if but basically short answers is the number of tracks available versus the number of track needed, right, per G cell. So whatever, for example, if the number of tracks is available is 10, and then if the number of needed is 15, then you have 5 overflow, right? That's the overflow, but so that's for short. But it'll be covered more in the next lecture 10. Lecture 10, I believe. No, actually, lecture 12 topics in congestions.
Okay, so the next question, you have a few minutes, is that if we have a design, why do we need blockage to stop what will be placed? Is it because the tool will do most things? If so, what will happen to the part that mean to place in that place?
Okay, so well, blockage is meant for us to use to fight congestions, right? To prevent cells placing where we don't want it to place. For example, a total blockage, right? We speak about total blockage. If we don't have any blockage, I mean, you can start out without any blockage, right? And you go through the first placement, and then you see usually around a macro corners, a bunch of cells there. Then you have congestion because around corner, there's not much around resource, right? So you go through first time you go through it, the tool place wherever it need to be, right? But there are times where there are too much density in one area based on connectivities, based on timing driven strategy, then it's too congested. Then the tool won't, and then you won't be able to route. So that's where you want to use blockers to tell the tool to to not to place many cells here or not to place cells there, basically to control congestion, to help you fight congestions.
Yeah, so in general, the tool will do a good job, but this is a case that you help the tool because it really rely on your knowledge of your design. So this is something that the tool doesn't have a lot of, meaning it will analyze certain things based on whatever data it has available. But sometimes you have to help the tool. If the tool cannot converge, the tool is just a tool. This is why you exist, right? So the tool still need human intervention, and you will help the tool say, if this area needs some blockages, then it will help with congestion and with routability and with timing, then you do that, right? So like Bart said, you don't need it until the tool needs help.
Yeah, exactly. So as far as like especially the soft blockage, right? In soft blockage, you want to put it where a lot of time between the macros where there's longs route that you don't want any cell to be placed there in the first place because take up routing source, therefore you have a lot of congestions. Okay, well,
Very
hopefully
good question. Thank you, Nguyễn Lê Minh.
Yeah. So good questions. Keep them coming. Okay. And we pretty much run out of times for these sessions. I appreciate all the questions and all the chime-ins from Phil, Wu, and Ting. So we'll see you guys next time.
Xin chào.
Yeah, thank you, anh Bạch.
Hẹn
Okay.
gặp lại. Yeah.
Bye.
Okay, bye bye.
The recording has stopped.